So why are we worrying about this? Well, security hinges on where it is. You may recognise those buildings. Those organisations are very concerned that for some of their operations they do them securely. Conversely, some of us are very concerned that we do our own operations very securely, so they don't. On our everyday level, providers of data centres, big companies, we are concerned that the code on those servers is secure.
Sorry.
Okay, thank you. I'd hate to suggest the first two organisations were responsible for those words not making it onto the tape.
That's how we get security.
Yeah. So, databases, data centres, we want the code in there to be secure. Oh, wrong button. And then, of course, the ubiquitous smart card, whether it's your bank details, there's this example here, your medical details, or your transport details. You don't want your bank account being broken into. The train company doesn't want you taking free rides on the train. So at the very smallest level, as well as the great big data centres, security matters. And when it goes wrong, first of all, when someone hacks an internet toilet, it's quite funny. When you discover that Osram's latest light bulb has about a textbook description of how to get security wrong in every hole in the book's there, and it happens to give a nice open hole into your home network, we start worrying. But then we get this. You'll recognise the Chinese webcam and the Myra botnet, which took over, which managed to issue some very important security attacks by taking over internet-connected webcams. And at that point, security stopped being fun or a bit of, oh my God, so this really does actually matter. And it matters particularly because of what is known as the Internet of Things, perhaps more correctly, the Internet of Sensors, but the fact that increasing amount of sensed information about your environment is connected to the Internet and can leak out there. So security becomes more and more impinging on our everyday lives. And some of the attacks will affect us. The ability to power cycle all the heating systems in the country and then take out the national grid so that no one has any power means people die on operating tables. So why the compiler? This is, although it's the LLVM dev room, the techniques I'm talking about are entirely generic. So I've put two well-known free and open source compilers there, LLVM and GCC, compiling to run on a computer. And increasingly for Internet of Things, that may be a very, very small computer. But why the compiler? Well, your C or C++ embedded code will go through the compiler. Even if you have something like Java, which you think of as sort of being interpreted, it's interpreted via a bit code, and something like a compiler is going to generate that bytecode. And even your assembler goes through the compiler. Almost all code goes through the compiler, the exception probably being the sort of scripting language that is source interpreted. And for those in the legacy place, people who actually write hexadecimal machine code and just put the numbers in their machine. But the point of using the compiler is security is a whole system problem. And on the whole, the compiler gets to look at almost all the code. So it's a very good tool. If you want to see, is my code secure, the compiler is quite a good place to put that functionality. So let's have a look at some of that. There's two ways the compiler can help. First of all, it can tell you if your code looks like it's doing bad things. It's a helpful assistant. It's warning you, this looks bad. Just as the compiler will today warn you, you appear to have an argument to your function that you're not actually using. Did you mean this? So there's that warning role where we can help. And secondly, there's the heavy lifting role. There are some very well known and established secure programming techniques that don't get widely used because they're a right royal pain to actually code up. And the compiler can help by hiding some of that for you. So, we've talked about this before. My colleague Simon Cook, who's in the back of the room over there, spoke in the LLVM developers meeting about using LLVM to guarantee program integrity, and that's all part of the security thing. You can only really talk about the security of your program if you have some confidence about its integrity. And that was really addressing how to deal with specialist hardware that provides some sort of support for instruction integrity and control flow integrity. And in order to do that, the compiler needs to understand that and write code that matches that. And he talked about the attribute protected that we've added for a production compiler for one customer that does exactly that. I'm not going to repeat that because you can watch that on the LLVM dev meeting videos. Some of the things that we've already done are very simple. Here is my security program, at which it becomes clear I'm not actually a security programmer. I've got a function called mangle, which obfuscates my secure key by reversing all its bytes, all its nibbles. So there it is. I give it an argument k, and it returns a value with all the nibbles swapped around. And that's great because then I can throw away k and no one will guess what my original key was. So let's have a look at how that behaves. Well, there we are in the main program. I've given it a string as an argument, which it will convert into a value using a to I and pass it to my argument, and I've got some arguments. So let's have a look what happens next. So we go in and we call our function, and there's our key because that happens to be dead beef in decimal, and our initial value of res is 0, and then let's go round the loop and get to the end of that function and return. And so we've inverted all the values and we've returned it, and so kn, our output there from the mangle function, is dead beef spelt backwards. And that's it. We're back in main, we've finished our program and we've thrown away our key. Except we haven't, because we've left it lying on a bit of dead stack. Now when we next call a function it'll get possibly wiped out, but it's sitting there lying in memory. And if I do something evil, which on this particular architecture is taking the address of my local variable and looking a couple of words further on, lo and behold, I can suck out my original key. Now, the simple thing we can do is something like this. Let's have a new attribute called erase stack. An erase stack adds to the epilogue of any function a small piece of code which just writes 0 over the entire stack frame. So now when I return, I can help myself to the next arrow. It's just been zeroed. And of course you can then generalize that. It doesn't have to be 0. Let's give it an attribute with an argument and we can turn it all into alternating bits. And indeed, all of those are fine. You'll just find various things going on. You can even go one further and have a randomized stack thing, which just writes random values on the stack. That has what may be a benefit in that if you've got the sort of code that's roaming around off the end of the stack, it's probably going to behave erratically because it's going to be picking up random variables. That may be a good thing, or you may be in the category that says, I don't like debugging programs where they deliberately behave differently every time I try and look at them. You take your choice there. That's a straightforward thing. That comes in the category of something we've done. It's not currently in a public compiler. One of the things that we do is we work for a lot of customers, writing them LLVM and GCC compilers for chips that are not yet out there, and therefore they don't want us to talk about them or go public because they don't want to spoil their big hit when it all comes out. So this exists for a processor that, if I told you about it, I'd have to shoot you all. Now that's been recorded as well. So let's go a bit further. So that was about solving one particular function. What about set jump and long jump? So here we are, I have my top function and it calls a load of functions and it goes through something called middle function, which takes which happens to have a key in it. Because all my keys are called K, 32-bit key, and eventually gets to the bottom where it's got its jump buffer, and it does a long jump back up to the top. So here we are, we're in farfunc, all's going well, and there's my cryptographic key sitting in my middle function, and then I return, and now I've still left my function in the middle. Now, unless all my functions have been labelled with the attribute clear stack or randomized stack, erase stack or randomized stack, I'm not going to get rid of that. And indeed, the way set jump works, it does typically work by just going back to where you started from. It's not going to unwind the stack anyway, so none of that's going to work very cleanly. However, since we know where we came from and where we're going to in long jump, there's no reason in principle why long jump couldn't wipe out its entire stack. Now, we could do it by having a special long jump function, long jump secure, that added that code, or we could have -f erase stack, which just says whatever the function, or even if it's a long jump function, erase the stack as you return, so you never leave stuff lying around on the stack. Or you could erase it to a particular value, or you could erase it to a random value. And that is all fairly straightforward. We've done most of that. We haven't actually done the last bit because the customer we're working for wasn't terribly concerned about long jump. Because their coding standard means they don't use long jump, not because they don't care about leaving stuff on the stack with long jump. So, in summary, we've got two attributes, one in two variations, to erase or randomise the stack on return, or we can do it at a whole program level, which also sorts long jump with erase stack equals n, or randomised stack. That's all simple and not difficult to do. Here's a harder problem. Okay. Right, we have a customer who is really worried about security. One of the ways that you can attack a chip is you can take its top off and you can shine laser light on it, very high laser light, and every so often you're lucky and it changes a value in memory. And you can observe how the chip behaves, and that tells you stuff about the chip, and indeed allows you to break its security. So you see strange things like this, where I set a global variable to a value, I go and do some computation, and then I go and test that the global value hasn't changed, even though patently it wouldn't have normally. And of course the compiler understands that. Now if I compile with O0, you can see the test, there's a little branch in there afterwards where it checks that the thing it set before hasn't changed from what it set it. But of course as soon as I turn on optimization, the compiler says, this is a stupid test, I know it's that value, I don't have to do it again. And the optimizer has carefully taken away my clever bit of secure code. Now, I can sort of fix that by saying, well, globvar is actually a volatile, some sort of dynamic register, so it makes sense to read it again. And then, if I compile, I will get my branch back. The problem is, I've now made my globvar volatile, and if that's the one place I care about, I've gone and hammered performance across my whole program for the sake of getting that one right. The question is, and this is where this becomes not what we've done, but what we'd like to do. Actually, how do we do that? Do we have to go down the route of pragmas around code to say, this particular fragment of code mustn't be optimized away? I hate pragmas. They're not syntactically particularly rich, but I don't know a better way of doing it. If anyone's got a better idea.
Yeah, there are attributes.
Yeah, okay, yeah. Yes, I've got 3 better ideas.
The Linux kernel actually has a couple of macros for this that cast a pointer to a volatile pointer and then dereference it, which has the desired effect. They're used for some concurrent programming that needs to say this might be changed behind your back by another thread.
Excellent. Okay, so that for the audio, that's the point that Linux has macros which hide a cast to a volatile and back again, so it's just on the local stuff. So that's a good approach we could.
Access once.
Access once. Okay, that's useful. I wasn't familiar with that. So that's the sort of thing that we can potentially do there. Okay. We're already getting value out of this meeting. This is intended to be a two-way discussion, this, because it's the start of the project. If you come and tell me that when we've finished the project, it'll be disappointing. So, let me tell you about this project. This is an academic project. It's funded by the British Engineering and Physical Sciences Research Council. It's a 4-year project. It's led by Professor Elizabeth Oswald and Dr. Dan Page at the University of Bristol, who for a long time have run their the computer science department's unit looking at information leakage. 4-year, it's got a team of RAs and PhD students, and Paolo, wave your hand. Paolo's going to be one of them, so he'll be able to tell you about it in the future. There are still vacancies in fact. If this is a field that interests you, there are still academic vacancies going at all levels, I understand. Embercosm is what's called an industrial supporter. It doesn't mean we get any of the money, but it means we've written to the government and said you really ought to fund this research project because it matters to industry, and furthermore we're going to be employing people to do this and so forth, and we really care about it. And one of the ways we're supporting it ourselves is we're taking the PhD students who work on that project. Some of them will come into us for PhD internships in the summer to do the information transfer thing, expose them to real compilers and so forth. And we have a role beyond that where some of the time spent, not so much by me, but people like Simon and Ed and Andrew Burgess and Graham Markle, is on actually implementing some of the things I'm talking about and implementing them in a general way to get them into the open source community for mainstream processors, not for top secret customer ones. How many people here would think they know what information leakage is? Right, good thing I haven't wasted these slides then. So Wikipedia actually is quite a good definition, which is what happens when you have something that's supposed to be a closed or secure system and an eavesdropper can learn stuff about it. And an example from the Second World War is the Japanese used secure radio transmissions which the Americans hadn't cracked to talk to their warships. However, they'd always transmit from a different station depending on what they were doing, and the Americans were able to learn what was going to happen from which station it was that was transmitting the information, and that's an example of information leakage. A technique that's very popular, was made popular about 10 years ago by Simon Moore and his team at Cambridge University, is differential power analysis. So power analysis is about looking at how much energy a computer uses. Differential power analysis is about looking at how that changes into different circumstances. And one of the things you can do is to look at how power changes as I try different ways of encrypting or different values for encryption and decryption, and learn stuff about the encryption algorithm and so forth. So here is a very simple algorithm I've got which takes my key, and if it's an odd key it subtracts 1 from it, and if it's an even key it takes the square root of the key. And clearly one of those is an easy operation and the other is an expensive operation. And if we run that, we can see that if I do my program and apply it to 7, I use about 25 microseconds of time on my laptop. And if I do it with an even number, it takes 86 seconds. And I could explore a lot of numbers and I'd come to the conclusion that this algorithm did something different for even numbers than for odd numbers. So that's a very simple example of differential power analysis. And what is it that was the mistake? It was fundamentally this. We took our critical variable, our key, and we let it control where the flow went. It's in an if statement. And now anyone who writes secure code knows that if you're worried about security, you don't have your critical variables controlling branches or loops. And that's easy to do. But if it's a big program and it's tired, and you're tired, or it was someone's birthday and you had a couple of pints at lunchtime, you might have got it wrong. So, how can we help? And we don't need to just worry about data-dependent control flow. We need to worry about data-dependent instruction timing. You may think there's no change to the control flow, but if the value affects how the instruction times, that'll affect it. Or even data-dependent memory access. Well, if it's this value, I go to RAM, and if it's this value, I go to flash. And flash and RAM do not have same energy profiles. So, here's my function of concern. One option is this, which is to say my argument K has an attribute which I've called critvar. Remember, I should have said we're now in the territory of stuff we want to do, not that we have done. So this is where feedback is welcome. Well, now hopefully I'll be able to get a warning that says, hold on, you've got a critical variable controlling a flow, because I can see it's part of the expression controlling this if statement. So that seems to be okay. And even if I put my critical variable in a header, because I'm including that header, I've still got all the information, I can still make that work. The critical variable usage is pretty obvious in those circumstances. But it's not quite so simple. What about this not so simple case? Because I actually assign the bottom byte of K to B, and then I look at B. Well, yes, I probably ought to be able to get that right and spot that B, although it's not the actual critical variable, is directly connected to the critical variable, and it's still a bad thing to do. But to do that, I need to understand the local data flow. Okay? So this is not something we're going to solve by a simple look at the program. We've got to understand the proper data flow through the program. Now, what about this case here? I've got two source files. One is func1, which has an argument as a critical variable, and it calls func2, passing in K. But func2 has nothing to say that its argument is a critical variable. It might be used in lots of places, some of which are not critical variables. So I go and compile it. I compile each and then I link them together, and I don't get any warnings because individually neither of those compilations can see a critical variables being used to control flow. And so the only solution I have is to go and use link time optimization. So this is something that has to go in an LTO world. And indeed, yes.
Have you thought about using the data flow analyzer to do this? I mean, if you're happy, as long as you're happy to check at runtime, you could use this to tag a bit of memory and then see how it propagates with the program.
So this is using runtime data flow tagging. I think that's a very good idea, and we haven't explored that, so it's on the tape. Another one to take away and look at in the investigation. And Paolo's listening over there, so one for him to look at. So yes.
I mean, you could request that func2 also has the attribute, right?
Yes. Clearly, if I put func2 had the attribute, that's fine.
Well, it might not need for all cases, just for that one case. It might be like a power of 2.
Yeah.
That you happen to need power of 2 for your key, but not for everything else. And then how do you do this?
Yeah, but you need different...
You can specialize, or you can do like const analysis. Is to say, look, this is a const thing, you're calling a non-const function, try to do some casting.
Yeah. So exactly. So the point being made for the tape was func2 might be used multiple times. So just making it a critical variable all the time may be inefficient if it's used widely in a non-critical context. So the point is that critical variable usage needs to understand global data flow, and that's generally true of security and its sister discipline of safety, which is two sides of the same coin. That generally they're whole system problems, and you need to look at the whole system. So data flow or runtime instrumentation, those sort of techniques are going to be what we need. So in summary, on this one approach of critical variables, simple cases are easy. Most cases need data flow analysis, and that probably means LTO or, as we've heard, runtime analysis for programs of any size. Now, I have this question: what if we get it wrong? If I tell you this is controlling a critical variable and it turns out actually I've made a mess of the data flow and I've been too cautious, I'm going to spend ages tearing my hair out. Where the hell is this wrong? It's not wrong. The compiler has actually not understood what the program's doing. False negatives mean some bad code may be getting through. But if I didn't do this at all the bad code would be getting through. So I think we need to aim on the air of false negatives are less of a problem than false positives. False positives could waste an awful lot of time.
It depends on the case. If this is a very security sensitive thing, then you want all the false negatives.
All the false positives. Yes, I agree.
If this is my toy stuff, then I don't really care about any of that.
True, yeah. Well, I think that's a good point to make. But certainly for the immediate term, I think we're going to try err on the second side. Of course, the idea is never to get it wrong, but we might not get there first time. And it's worth laying around, as I said before, it's not just control flow that leaks, variation in memory access, variation in instruction time I mentioned, and don't forget energy. Now, some of you know from previous talks, we've done a tremendous lot of work on the compiler's impact on energy consumption. Here's a graph from James Pallister, who spoke here a couple of years ago. This is a well-known 8-bit processor where we multiplied every pair of 8-bit numbers using their multiply instruction and measured how much energy it used. From this you can see they've implemented a 4-bit booth multiplier. I'm sure they didn't realise that their Verilog was quite so available to everyone. if I'm writing secure code using multiply, even just using the multiply instruction, the values going in are going to leak information. If anyone knows why 1 times 19 is the most energy efficient multiplier, I'll be interested. So that was about the first category, warning you about things that look bad. This is about the heavy lifting. And the heavy lifting, the heavy lifting is about making life easier. So here is a technique called bit splitting. And the idea of bits, one way you can find out what someone's cryptographic key is, if they put it in a nice 32-bit block in memory, you slice the top off the memory chip, you run your thing under a scanning electron microscope, and you read out the memory values. And you look for all 32-bit sequences and look for anything that might be a key. One way to solve that is to put little bits here, there, everywhere, all over the place, and then it's much harder, and that's called bit splitting. Now here I've just done byte splitting. I've taken my 32-bit key, I've put it in 4 variables, and I'll make sure my linker scripts put those 4 local global variables in completely different places. And then, of course, I now need a function to add 1 to that, where I add it to the least significant byte, and if that overflows, I add it to the next significant byte, and you can see just that is tedious, and that's just bytes. So the idea is you spread the key through memory so it can't be scanned for. That ought to work, but it is hard work. I'm just, adding 1. Look at the code I needed. And the problem is optimizing compilers are very good at spotting those patterns. And they say, gosh, this is really clever. I can combine this into one 32-bit variable. I'll save it somewhere. So you may have got your 4 bits, and then there's another bit of memory that has your 32 bits joined together. So the brilliance of the compiler completely scuppers us again. So one of the suggested approaches is this, is we give yourself an attribute bit split, and then you can just write k++, and the compiler will worry about that. And the compiler can do the mind-numbingly tedious one, if you want, of putting every single bit in a different location. These techniques don't do anything for performance, but that's not the point. I don't mind spending some performance if I'm going to get it. And it's trivial for the programmer. The compiler can actually do a really good job. It's all too easy when you write those complicated things to either make a mistake or, more importantly, accidentally to still leak information because you actually kept intermediate values around that were a bit leaky. Because it's inside the compiler, we can make sure the compiler knows if it's labelled bit split, don't go and stick it together. And it's still a whole system problem, so we've got to do it on a global basis. Oh, I thought there was one more slide there. So that is definitely on our radar as an early one to do, is to implement automatic bit splitting so you can write secure code and have it come out. It has the same issues, of course, of is it always possible, does it get hard and so forth, but I think that one probably we can solve.
Big endian, little endian.
Big endian, little endian, you name it. Yeah, I mean, it's got a whole can. We are planning to try and do this for a range of architectures, not everything for every architecture, but to prove it across architectures. And indeed, given the audience, be a bit careful to do it for GCC as well as for LLVM, because that's a good test of have you really got a general approach.
Would it not make more sense if the library implementation, at least for the bit splitting part?
Well, it is until you pass the argument to the library as a 32-bit value. And the answer is yes, there's balance, and the way it is often done is as a library. There is a balance all the way through, and in some sense you're putting the library like an intrinsic inside the compiler. So yeah, so I think these are good things. So for the record, that's saying, can you not do this as libraries, and or as some sort of intrinsic which brings the thing into the library. I think those are all good approaches, and it may end up that this maps down into a library called intrinsic, just as when I copy a struct, it maps down into the intrinsic bit mem copy.
We have to be careful not to get in line during LTO. They're already calling for the other.
Oh yeah,
and
yeah.
then you get back to the original place.
And we start to see why this is a 4-year project. So yeah, so these are all good comments, LTO inlining stuff and so forth. This is not the only stuff. I've touched on 2 because I want to give you a flavour of what we're trying to achieve, but we have some others on our list. And the idea is that these will be the ones that we explore. We want to take the best academic research. The stuff I've talked about so far has been known about for years, but there's a lot of newer stuff, and we want to not have that big gap between the academics knew it 2 decades ago and people got to actually use it now. We want to shorten that timescale. That's the point of the link between the research and industry. Atomicity. I've never quite understand why it's given that name. This is about balancing control paths. If I've got to go down 2 halves of an if then else, can I balance the paths so they take exactly the same time? Hard for a modern out of order processor, possible though for smaller embedded processors that you might get on a smart card. Super optimization for minimal leakage. That's because we're very big into super optimization, and all problems should be given to super optimization to see if it can solve it. Super optimization can optimize for any criterion. Information leakage could be one of them. Algorithmic choice. One way to hide what you're doing is to use different algorithms for the same job at different times. And certainly for things where there are multiple algorithms, that's a way to confuse data flow analysis. If I had, there's lots of ways of taking a square root. If that program taking a square root used one of different 5 different algorithms at random, then that would spoil my energy profile a bit. This verges in towards our architectural side of things. Instruction set extensions. Can we actually improve the instruction set to make minimizing leakage easier? Now, we already have one customer case where actually the instruction set has been changed because of a realization of one particular part of the architecture was leaking more information than was desirable. So there is a feedback to the development group, and that's why it's always good to develop your compiler before you spin your first silicon. Develop the 2 in parallel because you can feed off each other. And the last one, instruction shuffling. I have a whole sequence of things to do, very predictable, but there's always a degree of scheduling flexibility. Let's shuffle them around and give you several different scheduled flavors to allow you to get different profiles coming out. And that's it. So it's an early stage project. I welcome any feedback, questions, and so forth. Right, question in the middle, yeah.
Something about you may not need to go all the way down full LTO to do some global analysis. So, for example, if you, I don't know if you're familiar with ARM build attributes, that you can the way ARM deals with a lot of compatibility concerns between the thousands of different ARM variants is you annotate the binary and say this object, this takes, say for example, soft floating point, this one's hard floating point, and the linker can then basically flag between just at the attribute level and say these things don't match, I'll throw them out. So you might not need to go all the way down the full LTO if you can say the function that with these functions.
So this is the suggestion that we don't need the full LTO level. We can use things like the ARM build attributes to annotate binaries to give enough information that we can get that sort of thing right. Yeah.
A small remark about the balancing. So unless you have unless your microcontroller has no cache at all, as soon as you have a balance between 2 code paths, and one goes on one cache line and the other goes on the other, as soon as some other code evicts one cache line, you can measure again the time. I'm an academic, so at one point we investigated this and we just executed conditionally all instructions.
Code balancing is almost impossible. As soon as you go cached or out of order or any of those, a lot of the very smallest things, when you're looking at the Internet of Things, the smallest, those processors have no caches or they're in order, uncached machines, right at bare bones. But I agree with you. Once you go into that, you're sort of losing information all over the place there. So you're sort of solving the same problem. Yes. Sorry, for the record, the question was about how cached architectures shuffling is not going to, balancing is not going to work. So.
From a hardware perspective, often the technology to improve are jittering or masking or other variables. Do you want to look into that also, or is this something unique to the hardware?
Because the areas we tend to work in, which are deeply embedded and we're often pre-silicon, we're very interested in that. It's not a primary goal for us to look at architectures directly for this project, but the potential of the compiler to inform architectural decisions and engage with the hardware engineer is absolutely something we want to do. Yeah.
So actually, follow up on the dash line question. You have, I assume that like bit shifting, the bit splitting or the byte splitting is targeted at small embedded processors without cache. If not, you of course you introduce conditional data access again. And actually, you need more info on your key, like a side effect, like if you implement.
Yeah. So.
Which caches are
So this is a comment about once you have caches and you have to worry about caches, then bit splitting ends up with having other differentials. You're right, it's aimed at the very smallest processors. I think there's a very open research question of how do you make bit splitting work in the context of cache lines and so forth without leaking more information than you're trying to hide.
So you're deleting the stack thing. I'm wondering why you didn't set the attribute in the variable itself, because then you only need to zero that one variable, and then that works with malloc stuff as well, and you can you don't need to worry about long jumps, set jumps. You don't need to worry about erasing huge stacks. Some people do like huge stacks, and you can also do this in the heap.
So the question is, why don't we just do erase stack on the individual variable rather than worrying about flattening the whole stack? The answer is because we hadn't thought to do that. When we had the conversation with the customer, flattening the whole stack was one there. And interesting, the feedback afterwards was, well, we're not sure we're going to use it because now we have to get our compiler revalidated because you're affecting the security of the code generated. So it cuts both ways. Yes?
Or we also want to clear the registers, not only the stack.
Yes.
So the comment is on erase stack, you probably want to erase the registers. And in fact, I believe the implementation we have actually does erase the registers as well.
Yeah, you erase the rest and then move the rest into memory.
Yeah.
If you've got different register widths, and you can end up overwriting parts of those, but you might need to somehow clear the top part of registers.
Yeah, and comment about it might get a bit harder about clearing halves of registers if you have variable size registers. More questions? No. Thank you all very much.